So it'll be secant squared y what? Times dy dx. What's the that's the product rule. All right? So it'll be minus, now here's where people this really sucks. When there's minus the product, that negative has to go to both pieces of the answer. You've seen this a lot in math, where you forget to distribute that negative. Maybe. It's happened to you in the limit definition of functions. You forget to distribute that negative in the second part. Oh, shit. So I'm going to do this in here. What's the derivative of x? 1, Jeff. Great. Plus x. What's the derivative of e to the y? E to the y times dy dx, because you just took a derivative of something with a y in it. There's an inside function. That inside function is y. I'll do this way. Yay. And now it's got a nice, there's only one thing that's in the wrong place, right? Yes? No? What's in the wrong place? What does not have a dy dx in it that's on the side with the stuff that has a dy dx in it? Yeah, that guy. So it's minus e to the y. So let me add it. So I get secant squared y dy dx minus x e to the 1 dy dx equals 4 plus e to the y. And then you do this, you take the dy dx out, so I end up dividing by the shit that's with it. So I get dy dx equals 4 plus e to the y over secant squared y minus x e to the y. Jambalaya. My y's are really looking bad here. Coolness. So what's the slope at the point, what did I say, 0 pi? Is that a point that goes through? What's tangent of pi? What's tangent of pi? What's on the top of tangent? Tangent is what over what? Trig functions. Sine over cosine. So tangent, this isn't perfect, but tangent basically goes like sine. It's big when sine is big, it's small when sine is small. So what's sine of pi? I love you guys so much. Hopefully you guys, yes. 0, yeah. So what's tangent of pi? 0. So this is 0 minus 0 times, who cares, equals 0. So yes, that's a point that goes through. It also goes to the point 0, 2 pi. It also goes to the point 0, 3 pi. It also goes to the point 0, pi. Cool. So obviously it's not a function, right? So how do I find the slope at 0 pi? What's x? And what's y? And then you just plug them in. So the slope, here's how we kind of designate that with this notation. The slope at 0 pi is 4 plus e, is it 0? Yeah, 4 plus e to the pi over secant squared of pi minus 0. Ooh, I love that. What is secant pi? What's cosine pi? -1. So secant pi is -1. Squared is 1. So I end up with 4 plus e to the pi. That's one of the coolest slopes. I love it. So you will see problems that say implicitly find dy dx. Then they're going to say find the equation of the tangent line at 0 pi for that function. Oh shit! So then we got the slope, and then we have to plug it into y minus y1 business, right? Actually, this is kind of nice because this is the y-intercept. So you just use mx plus b. Okay, you guys are excited about that prospect. Let me see, what was it? There was something. Oh, yeah. Oh, shit. Find the derivative of inverse sine of x. Oh, shit. We can finally do this. I know you've been like, when are we going to do derivatives in the inverse trig functions? Jeff, come on. I know, you haven't. I understand. So try to reason out why I had to wait till now to be able to do this. Right? So here's, let me bring in, so we got y equals this. Okay, I don't have a freaking clue. Do you want to use the limit definition? If you do, go ahead, do it on your own. I don't want to use limit freaking definition. How can I rewrite this? If y is the inverse sine of x, what's x? How do you solve for x?
Sine y equals x.
Yeah, you take the sine of both sides, right? I mean, how would you solve y equals cube root of x? What would you do? You apply the inverse function to both sides. So here, how would I solve for x? Apply the inverse function to both sides. Take the sine of both sides. So here I get sine y equals x. Find dy dx. Do it. Now we can do it. Now you see why I had to wait till now. Find dy dx for this. We're going to figure out what the derivative of the inverse sine or arc sine, depending on your teacher. I always hated arc sine, but oh well. It's up to you. Take the derivative. We know how to do it now. Here, I'll do this side. I did half of it. Come on. So funny, Jeff. Keep my day job. I understand. So what do you do with that sine? Derivative of sine is cosine? dy dx, I like it. So dy dx is equal to 1 over cosine y, which is also known as secant y. This is no good. I don't want that. It started with a function of x, right? So I should be able to figure out the derivative as a function of x. And here's where the little thing on the warm-ups comes back. When I wrote y equals inverse sine of x, I can draw a triangle. Draw a triangle. Right? In fact, even looking at this, the sine of y equals x. So if I put the angle y is an angle. How do I know that? Because it's inside sine, that's why. What can I put this? Where can I put this? And there's something else I could put somewhere too. And you're like, yeah, I could tell you where to put stuff, Jeff. Where would x go? What sine? The ratio. Sine is the ratio of what to what? Yeah, the y piece to the hypotenuse. I like it. You know, SOHCAHTOA, great. That sucks, but it's okay. So this would be the y piece and the hypotenuse. Hey, and what's this need? This needs the secant of that angle, which of course is related to the cosine, right? So what piece am I missing then? Can I get the cosine of y with what I have up there? What's happening right now? So what does cosine need? What side does cosine need? Sine needs the y side. Cosine needs x side. What kind of triangle is this? Right. Yeah, it's got to be a right triangle because I'm using trig directly. So what's this side then? What do I use to figure out this side? I don't need any trig for that. I need the... Yeah, old Greek dude comes back in. So what is that side? This should almost be second nature. You shouldn't have to even set it up. It's the square root of everything minus the square of the piece. Right? This is made up of these two added together. So this one would be the square root of this squared minus that squared. So what's this? Cosine is this side over that side. So secant is this side over that side. So you get this. So the derivative of the inverse sine is 1 over the square root of 1 minus x squared. Nothing that you would just guess, I don't think. And you can do something very similar for cosine, inverse tangent, so forth, right? I think, I can't remember if I signed it in the homework, but you can see a little table at the bottom, page 214, for all those. I normally don't make people memorize those, but if you're going much further in math, you might as well just take the time now to memorize those. Okay. Oh, one last thing. Not even a last thing. That is the next section. That's beautiful. I love it. So one last thing for today is the entire next section, which they could have actually just made a part of this section. We just proved the derivative of the inverse sine. You could do the rest of them if you want to, and they're all in that little table. Same way. You do the same way. There's another function that we don't know the derivative of that it's kind of related to stuff we've done. We know the derivative of e to the x. And now we've got this implicit method that helps me figure out derivatives of inverse functions. And of course, what's the inverse of e to the x? What's the inverse function of e to the x? You better not say e to the negative 1. I'm going to have to do something that I'll regret. What's the inverse function of e to the x? Natural log. Okay, I like it. So we can use this method to figure out what natural logs derivatives. There's actually a problem in the homework that makes you graph what the answer is. So here's natural log, right? And then you have to graph the slope of this. So if you've done the homework, you've done this. What's the slope of this look like? Well, here it's really big.
Then it gets smaller.
Every time I turn around, I'm like, did they leave? That's really big, positive. And it keeps getting smaller and smaller, but it's eternally positive. Do you see that? But it just keeps getting smaller and smaller positive. So really big positive, and then it's, oh, Jesus. And then it's getting smaller and smaller positive. What does that look like a part of? I put this little mirror image here. Somebody know what that is the graph of? No, here's natural log. What is this the graph of? 1 over x. Yes. So that's not a proof that it is equal to 1 over x. Maybe it's 1.78 over x. I don't know. But it looks like it should be something over x, the answer to this. So let's see if we can figure out what the derivative of a natural log is. So here's this. What's the first thing I do since I don't know what the shit it is, and I have this new process, implicit differentiation. How can I rewrite this? What's the base understood to be? What's the base understood to be? What's the base of ln? What's the stupid way to write ln? The way that hurts me to write it. That is the dumb way to write ln, right? That is what ln represents. Why do we give it its own symbol and not even put the e there? It's the same reason we don't put a 2 in the square root symbol, because it's the most used one. And we like to save time because we're lazy, or frugal with our time, whichever one you like better. How do I rewrite this then? It's going to be e just, you don't want to speak? How do I rewrite log base 7 of y equals x? How do I rewrite that exponential?
So 2x equals.
Yes, okay, so how do I rewrite this? E to the y equals x. Right? Those are both equivalent. Go ahead and finish that out. Take the derivative, find dy dx. This is really quick, right? What is this sign? So you get dy over dx equals 1 over e to the y. But what was e to the y? E to the y was x. So you just get 1 over x, which is what we predicted for the picture. Yeah. Okay, maybe. Sure. Okay. Let me see. So, for example, the reason they put this in its own section is because all the log properties come back. So you got all these problems, all these different properties. Just to show you, if I would have done all this with this instead, this would have been x equals b to the y. The derivative of b to the y was actually this. I don't know if you guys remember, this was the adjustment for it not being e. We proved that before. So what you end up with is dy dx is equal to 1 over b to the y, which is x, times natural log of b. So there's that adjustment we should expect for the base not being e. If the base is e, the derivative is nice, because that extra shit goes to 1. So if I had, for example, log base 6 of x, its derivative would be 1 over x ln 6. The little ln 6 is the adjustment to the slope, since it's not e. It's not going through that point. Nice. Okay. Of course, if the base were e, this would just be 1, so it would just be 1 over x like we got. So now I can do stuff to you like this. Oh, what you got? Let's do this one together. I'm going to do this 2 different ways. I'm going to attack it the way it is, and then I'm going to remind you about some properties of logs. So the derivative of ln of something is 1 over that something. So the derivative of ln of this is 1 over this times the derivative of the inside. Yeah. Of course, what's the derivative of the inside? A lot, right? That's nice. That's nice. Now, I could also have done this like this. what's the properties I could use here? Because an inside could factor. You guys remember that? You guys remember that? That log property? Oh shit. So you got trig properties, log properties. The properties of logs have to be the same as the properties of powers because logs are powers. Right? The answer to a logarithmic question is the power you need. Okay, it's a power. So what do I do when I multiply things with like bases? I add the powers. That's all that property says. So if you never quite got that the first time around, that's all this shit is. You already know the properties of logs when you learn the properties of powers. So this way, if I do this, this is just derivative is just 1 over x. Derivative of this is just 1 over x minus 1 because the derivative of the inside. I want to make this point now. I haven't said this yet, but anytime the inside function is x plus a number or x minus a number, so it could be 0, then I don't need chain rule because its slope is 1, right? I don't know if you guys see that. I don't need to think about chain rule for that shit because the slope of that inside is just 1. Now, do these look the same? Okay, I like it. Yes, they do, because if I just get like LCD, I'd get here, right? So it really depends on what you're going to do next with a problem. That looks a lot easier to look at. This one I could find, for example, what would I do to figure out the horizontal tangent lines here? So this is step A, B, horizontal tangent lines. How could I figure out the horizontal tangent lines? How many are there? What do I look at? What does a horizontal tangent line mean? Happens. Slope is 0. I like it. There's a slope. How do I make it equal to 0? I love it. So set it equal to 0. I like the look on your face. You're like, well, Jeff, you set it equal to 0. Okay, but then, all right, now what? That's my real question. Now what? What's the only way a fraction can be 0? If the top is 0. So x equal 1/2. Bottom can't make a fraction 0. So that would be the location of the horizontal tangent line at 1/2. Like it. What about this here? Let me see. So if you attack this directly, that would so desperately suck. You'd have 1 over that shit times the derivative of that shit, which is a long-ass quotient rule. Oh my god. So this is one where I highly recommend you use log properties to rewrite it first, right? How do I rewrite the natural log of something divided by something? When I divide things with like bases, what do I do with the powers? When I divide things with like bases, what do I do with the powers? Subtract. So this is going to be the natural log, the power on the top minus the power on the bottom. Right, now I could do, actually I don't know why I'm doing this first. This will still work. I don't know why I'm making it. Well, screw it. I'll do it this way. Why not? I could have factored here, but I'm going to factor now. Is this cool? This would be x squared minus 1 if I took an x out. So it'll be x plus 1, x minus 1. Take an x squared out and then get x plus 1. I don't know why I did it this way. Oh well, too bad for you, Jeff. So then I get ln x plus ln x plus 1 plus ln x minus 1 minus ln x squared minus ln x plus 1. These kill each other. Where are you? Come here. There's still more I could do. What happens here? do with that too? What's the property of logs? The most important property of logs, to be honest. Yeah, the 2 just comes down. So you get ln x minus 2 ln x is negative ln x. Who else survived? Plus ln of x minus 1. And that's it. So all that shit became that. They could have factored first. It would have probably looked a little better, but oh well. And now I can do the derivative. What's the derivative of this? Y prime equals negative 1 over x plus 1 over x minus 1. Yay! But my God, I have a special place in my heart for those people that just leave it like this and start to, oh my God, I don't want to do that. So basically, before you take derivatives, now that we've gotten past all the individual, remember like in product rule section, I said you don't want to FOIL, they want you to get used to the product. Now it's just simplify as much as you can before you do derivatives. Hopefully that kind of makes sense. The less you leave simplified, the harder the derivative is going to be to do. Okay. Let's see. Is there something else in here? Blah, blah, blah. Blah, blah, blah. Blah, blah, blah. Oh, here's one last thing about this. I don't want to. Yeah, I guess I can do it. What's the problem when you look at ln x and 1 over x, right? That's this guy's derivative. What's the domain of this guy? Where's an asymptote for this guy? So what's the domain of this guy? Yes, 0 to infinity. What's the domain of this guy? Yes, negative infinity to 0, 0 to infinity. So do you see how there is a problem with saying that this guy's derivative equals this? It kind of, the domains don't really match. So one thing is, if you do have this, the domain of your answer can't be all, it's got to be just that. Because it came from a function that doesn't exist for negative x's. So the domain of your answer actually has to become that if it came from a derivative of ln x. Because could I use negative 2 in the first place? So why could I suddenly do it now? No, it doesn't make any damn sense. But what it becomes more interesting is this, the derivative of this guy is this. Now the domains match. Okay, maybe. This is going to become a lot more important when we start doing anti-differentiation, when we start doing the opposite of derivatives, also known as integration. If you take the antiderivative of this, you've got to have it come out to be natural log of the absolute value of x, so the domains match. That's when it really becomes a big deal. Okay. Remember. Let's see. Oh, is this where they do that? Yes. Okay. Since this came up, last thing. Somebody earlier asked about x to the cosine x. And I so desperately love that question. Not just because it's one of the few questions anybody's ever asked here, but it's a really good question by itself. Let's just tackle this one directly. I love it. So when I have a situation where I have a derivative I'm trying to do that I have no idea what it is, I need to rewrite the question and hope it becomes something I can do. So what can I... The fundamental problem is there's a functional base and a functional power. Now, notice when I am talking about this. I am talking about it right now. This is the first time I could really talk about this. And what did we just learn the derivative of? Natural log. So I bet you anything, I take a natural log of both sides. And what happens when I do that? What can I do over here? Bring the cosine x down. And then you can implicitly differentiate. So what's the derivative of ln of something?
1 over
1 over that something times dy dx. I like it. On this side I have a who to what rule? What to which? Who to what? What rule is this? Product rule. I love it. So the derivative of cosine is negative sine plus the derivative of natural log is 1 over x. I like it. What was y? That, right? I'm going to multiply both sides by y, but just to kind of cut to the chase, I'm going to multiply both sides by what y really is. Let me just do this. You see. So the derivative of something to a power is supposed to equal, oh geez, Jeff, what is your problem, dude? There you go, buddy. Something to a power is supposed to equal to itself, right? Fundamentally, are you guys with me? So that's kind of like captured. Now watch, this is really, oh, let's see if you guys are cool with this. I keep wanting to put that negative in here, I haven't done that yet. Oh, I desperately want you guys to get this because this so kicks ass. Oh, okay. Oh, you're enough for that. All right. You see the process of how to do functional to functional base to a functional power. The process is take an ln, use implicit. That's the process. I'm basically done. I am done. It is done. I'm going to keep going because I'm Jeff and I'm weird. But this is so awesome. Let me see if you guys get this. Let me write this up here. This is where things are going to get a little weird, but let's see if you guys are cool with this. Now let's see. Now watch. Are you guys cool with that? What's x to the power divided by x to the first? That power minus 1, right? You subtract power. So it's x to the cosine x minus 1 times cosine x. So if I look at this as x to a constant, wouldn't I bring the cosine down and then subtract 1? Isn't that exactly what the hell that shit says? Do you remember what I said earlier? It looks like you do both rules. And then what if I look at it as a constant to a functional power? So a constant to a functional power, its derivative would look like this, right? And of course times the derivative of the inside of its extra shit. So watch this. Here's my x to the cosine x times ln of the base times the derivative of the inside function. So the result, since you have a function that's got two different rules in it, the result ends up being the addition of both rules. It's really cool. Do you have to know that to do these problems? No. You take an ln, implicit, and you stop, and you say, Jeff is weird. Whatever, Jeff. But that I remember, it wasn't that long ago I figured this out. Nobody ever told me this shit, and it's just so cool. So I hope you guys sort of get it a little bit. Not really okay. All right. I think that's enough for today. I've thrown a lot of stuff at you. So Thursday I'll have the quizzes graded. I think oh shit. What is the test? Is it a week from this Thursday, right? I think. Yes, a week from this Thursday. So this Thursday I'll have the practice test. We're more than likely not going to make it all the way through chapter 3. So this Thursday we'll actually know better what the test is going to cover. How much or 3.
Are we going to have another quiz before then on the change, or is it just going to be on the game?
We got too much to